Okay, today we are going to share our today we are going to share our three speakers from different universities globally. Okay, one is from Saudi Arabia, one is from Europe, and one is from North America in Canada. So we are glad to have those nice and young and distinguished speakers with us today to present their research in the field of the optoelectronics. And all three guests, they are working on those optoelectronics for a while, and I think they have a very good story to share with you guys about their past progress and the future plans for the new research. All right, so let's start with the first one. Let me introduce myself a bit. Okay, I'm a professor right now in University of Science and Technology. I'm also working on the optoelectronics, including lasers, light emitting diodes, and photodetectors. And today we are going to have three guests working on the same field with me, and I hope you guys will enjoy our talk today. Okay, so let's start with the first guest. So we will welcome Dr. Dingding Ren to join us first to present his work with a very nice topic. So let me introduce about him first, okay? Dingding Ren is right now is a postdoc researcher at Delft University of Technology in Netherlands, and he was a full-time research faculty member from 2020 to 23 in Norwegian University of Science and Technology, and running a 3-year research project funded by Research Council of Norway to develop a low-loss photonic platform. And he graduated from PhD in electronics and telecommunications in NTNU with Professor Hedge Wellman in 2017, and since 2019, he was a postdoc researcher at Professor David Bogoff's group at the University of Notre Dame. Okay, let's welcome Dr. Ren first. Okay, so yeah, it's your time now.
Thank you, Heidi, for the nice introduction. I'll share my slides. Can you see my slides now? Okay, great.
Yeah.
Okay, I will try to warm up the platforms for the next speaker. So my presentation today, I'll talk about long wave integrated photonics. Yes. Firstly, where is long wave infrared? Let's look at black body radiation. Okay, from the sun, actually, it centered at wavelengths in the visible and gradually decrease. So it follows the law we call Wave displacement law. Based on the temperature, we will estimate the black body radiation. And also, our Earth has a temperature, so we radiate to the space. So this wavelength is about our body temperature, about like 20 degrees, 30 degrees. So it emits about 10 micrometer. So this 10 micrometer is well within the range of long wave infrared. If we look at the atmospherical absorption, we see actually there's a very opaque regions in the UV because the relay scattering. And in the visible, we have the first atmospherical window, so there's very little absorption. And gradually, this molecular absorption starts to kick in. And we have a second atmospherical window in the long wave infrared if we plot it in the linear scale. Here we see actually short wave infrared is from 1 to 2.5 micrometer, and mid wave infrared about from 3 to 5 micron. And our long wave infrared is from 6 to 14 micron. Okay, the short wave infrared and the middle infrared, we call it mid infrared. And the longer than 14 micron, we usually call far infrared. Are there any special usefulness in the long wave infrared? Okay, I'll show you what we can expect to benefit from long wave IR applications. We can take images using the visible camera or the long wave infrared camera. We can see in fog condition, actually the long wave infrared is much clearer than in the fog condition. If we look at the transmission spectrum, actually we see the longer we go to longer wavelengths, the transmission maintains very well in a fog condition. This is a clear shows in the visible, it's almost no transmission in thick fluor condition, but actually long wave infrared has very good transmission in condition weather. So that means long wave infrared may be a natural choice for all weather LiDAR applications, except for this all weather, very high transmission because reduce the relay scattering. Are there any other benefits? I would introduce, long wave infrared it provides fingerprint molecular signature for sensing applications. Why I'm saying it provides molecular signature because let's take graphene as an example. We know we need to use Raman spectroscopy to characterize the graphene. We shoot the graphene using a 532 green laser. Still, we need to collect the characteristic emission, the D peak, G peak, and G dot peak in the long wave infrared spectrum due to the inelastic Raman scattering. So if we know the emission spectrum from this long wave infrared, and we can identify, okay, this is exactly graphene. So long wave infrared is very suitable for sensing applications. Let's look at the a lot of chemicals. Our long wave infrared is from 6 to 14 microns. This wavelength range corresponding well to the intramolecular vibrations. If we see a lot of different chemicals, so all their intramolecular vibration locates in the long wave infrared. So this is a specific opportunity for doing high efficiency chemical sensing. What are the opportunities? We can do a hyperspectral image, right? Using the long wave infrared camera. We can basically use a filter to capture the green gas emission. However, there's not applicable to know what's exactly the chemical from this film. Okay, we know, okay, it's maybe CO2, but we don't know if it's some toxic or not. If we want to know the composition, we need a technology called Fourier interferometer spectrometer, FTS. However, the challenge is it's a bulk equipment, not compatible to the portable devices. Also, the light source is basically a glow bar. It's like a lamp heating up to thousands of degrees, and there is basically very slow mechanical mirror to move to scan the spectrum. So it's very slow, but it's a universal chemical identification facility. Actually, the laser spectroscopy would be fast compared to FTS. However, the one laser only aiming at one single frequency. This image shows Hitachi breath analyzer, which basically you do breathe and they will tell you whether you have some health problem or not. Inside this breath analyzer, there are three quantum cascade lasers. So they can basically analyze three emission spectrums. But it needs several lasers, right? If you want to detect multiple gases, it's quickly scale up the number of QCL. So it's not useful for practical applications. So I'm saying like long wave IR photonic sensing could be revolution if it could provide fast detection speed comparing to STS. It should provide real-time imaging sensing capacity. Next, it should be able to universal chemical identification. That means I don't need to identify one specific. I have the ability to sense a variety of chemical species, and also should be compatible with the CMOS technology. That means we can do chip scale sensing, right? We can put into our cell phones or on the drones for variety of applications. Are there any possibility to doing this? I would say yes. If we could combining the long wave infrared photonics with frequency cones, or to realize frequency cones in the long wave infrared. A frequency cones is technology that the light consists of a large number of evenly spaced lasers. It's not like single frequency laser. It's a multi-mode laser. But each mode of the laser, they have equally spaced frequency difference. What the benefit is like the different frequency could be in the radio frequency. Okay, doing a hydrogen detection, so we will be able to convert the optical frequency to the microwave frequency. That means we can do optical sensing and detect using the RF spectrum analyzer. So here I show a brief schematic about this dual cone spectroscopy. So we have two frequency cones. They are slightly the free spectrum range that have slightly different free spectral range. That means the lasing difference is slightly shifted. So one frequency cone is shining through a sample, and then we get the absorption feature. Okay, due to this frequency difference, the beat frequency is in the IF domain. So this absorption feature has already been well resolved in the optical domain and converted to the detection in the radio frequency domain. So we will have the resolution and signal to noise ratio of the laser spectroscopy, and the bandwidth about pulse source, and the no moving parts. That means we can do real-time chemical detection. So frequency cone is not a new technology. Actually, it has been awarded Nobel Prize already in 2005. Frequency cone is a beauty because it combines ultra fast optics with nonlinear optics. That means if you have very short pulse, you have very broadband signals. Broadband signal, we know, like if you want to do chemical sensing, we want a broadband signals. So last decades has also combining this frequency technology to integrate photonics. So what that brings about a combination between nonlinear photonics, integrated photonics, and ultra fast optics. So here we do this. They use actually the macro resonator on chip, basically balance the gain and loss. So by tuning the geometry about this micro resonator, they could do dispersion engineering that compensate the carrier nonlinearity. What they achieve is a mode locking laser on chip. Due to the very, very small volume about this macro resonator, they could get a really low threshold for this broadband solitone microcone generation in the telecom band. However, the problem for us to do sensing is like no microcone in the long wave infrared fingerprint region. There are long wave IR frequency cones, but they are based on quantum cascade laser. This is the first long wave IR cone. They use a quantum cascade laser to do the dispersion engineering about the gain structures. There's intra-band transitions in the quantum cascade laser, so I engineer the dispersion in the gain structure. However, we see actually they only get, for example, less than 20 lines. This is because the transparency window is very narrow. In my opinion, there is a contradictory between the requirement of a frequency cone and the lasers. For laser designs, we always want a narrow gain spectrum that we have efficient lasing. That will reduce the threshold. However, for frequency cones, we want a broadband gain. That's basically contradictory to the design of a laser. So that's why people have tried to use parallel QCL, DFB QCL, or even using a ring laser to do the frequency cone generation in the long wave infrared spectrum. However, you see only less than 10 lines. This is less than 30 wave numbers would be achieved for frequency cone generation in the long wave infrared. So still like no broadband frequency cone in the long wave infrared to do chemical sensing applications. So can we do what has been very successful in the telecom band, right? Like 1.55? The solution is not easy, okay? Because almost all materials becomes lossy in the long wave infrared. So this image shows a diamond passive optical micro resonator. However, they show only Q factor about 3,000. And this is like germanium silicon. So both shows very, very similar Q factor about 3,000. We need at least 100,000 Q factor to have this parametric oscillation, that means frequency cone generation in the long wave infrared. So if we look at the spectrum, we found like germanium may be a better choice for long wave infrared integrated photonics because the multiphonon absorption is the onset of multiphonal process happens at a very long frequency than silicon. So this plot, the blue and the red curve shows the absorption, the loss of the silicon, intrinsic silicon. We see actually the 3-phonal onset wavelength is about 7 micron. While for germanium, there is a wide transparency window below 1 dB per centimeter in the long-wave infrared. It also has very high refractive index, about 4. So that guarantee like we will have very high Kerr nonlinearity that reduce the threshold for parametric oscillator. So we start to develop a fabrication process to maintain the quality about the intrinsic germanium. Okay, we develop a wafer bonding, so we use nano plates to make a homemade wafer bonder, and which we have made a germanium insulator ourselves, and then we do the mechanical polishing and lamping, and do the e-beam lithography, and finally we have made this macro resonator of 5 micron in thickness in the long-wave infrared for long-wave infrared applications. So the images here I show you is a macro resonator made of native germanium, about 100 micron, 100 micron suspended to the edge, to the glass edge, diameter about 450. If we look at the F acid, it's very smooth, and so it should be a very little scattering loss. So we can also control the macro resonator, the position. So we place it to the chip edge, so that will be efficient, will be easy for waveguide to couple the light in the long-wave infrared to the macro resonator. So we have performed the finite element simulation. So this gives us an effective reflecting index about 3.88. We plot the free spectral range and the second order dispersion. We actually see from 7 to 10 micrometer, we have very low anomalous dispersion. This range is very good for frequency cone generation. To couple the long-wave infrared light into the macro resonator, we also need a waveguide, because there's no other waveguide, commercial waveguide available in the long-wave infrared. So we made the waveguide ourselves based on the same process, same fabrication process we developed for making the macro resonator. So the effective reflecting index is about 3.89, which is very similar for the macro resonator. So they can do very efficient coupling. The optical phase, they are matched. And they are also partially suspended. That means we have also good mechanical tolerance to do the coupling. We have built our optical setup to do the measurement based on DFB quantum cascade laser, and also a mercury cadmium telluride for the detectors. So the single mode DFB QCL gives us a 5 number tuning range. The macro resonator is mounted on a piezoelectric stage, so that we can change the distance between the macro resonator and the waveguide. They say we can do efficient coupling. So if we look at the already existing literature, you will find that the measurements in the long-wave infrared is very rough. Okay, this resonance only contains less than 10 points because the resolution of FTR is very, very rough comparing to the resonance. And this scan using external cavity contrast laser to characterize about Q of 3000. So if 10 times higher Q, this laser will not be able to characterize the resonance. And also, thermal tuning can do continuous measurement, but there is huge standard deviations. So we have used this distributed feedback quantum cascade laser to do the first continuous line, first off-free continuous line with measurement that scans lower resonance at long-wave IR. We can clearly resolve the waterlines and do a coupling study with the macro resonator. By dividing with the reference, we could easily get the free spectrum range about the fundamental mode from our MAC resonator about 51 gigahertz, which agrees very well to our finite element simulation. So this confirms that this resonance is from our MAC resonator. So we did both T and TM polarization fitting, and this full width half maximum is about 174 megahertz. So this gave us a loaded quality factor about 220,000 and intrinsic quality factor about 250,000. So if we compare the existing technology, we have almost 2 order of magnitude better quality factor in the long wave infrared. Yeah, so what's amazing is like the frequency cone generation, the threshold actually is inversely to Q squared, right? It's not linear, it's inverse to Q squared. So this gives us a parametric threshold about 240 milliwatt. So we know the state-of-art quantum cascade laser can give us about 1 volt optical power. So this is well within a range for doing frequency cone generation using a quantum cascade laser. So we have also performed solve the nonlinear Schrodinger equation. So using the parameter here, if we pump the MAC resonator about 200 milliwatts at a wavelength about 9.3 micrometer, we will get this dispersion curve, which have 0 dispersion about at exactly like 9.3 micrometer. And we see a clearly frequency cone generation in the simulation. So by detuning the wavelengths, we firstly see spectral broadening. We see actually frequency cone generation. And by further detuning, actually we undergo chaotic frequency cone. And by further detuning, there is a stable soliton regime that all modes they are locked to one soliton. So this gives us about like more than 20 terahertz bandwidth. This corresponds to about 100 femtosecond ultra short pulse in the long wave infrared. We see, okay, we use the waveguide. Okay, this is a problem. Why we don't get the long wave infrared frequency cone yet is because we use the germanium on waveguide. This gives us very high loss, about 9 per centimeter in the long wave infrared, because glass substrate is very loss. Gives a loss more than 10,000 per centimeter. So if we want to have low loss waveguide to efficiently couple the optical signal into the waveguide, so we have to develop another platform, germanium zinc selenide platform. If we look at the loss curve about the zinc selenide, at long wave infrared, it's almost no loss. But the problem for zinc selenide is it's very difficult to fabricate. It is not compatible with the CMOS technology. So we have basically developed a process to combine germanium on zinc selenide that makes the long wave infrared silicon insulator, in my opinion. So the germanium is bonded on the polycrystalline zinc selenide wafer. We have performed the transmission measurement, and from this Faber-Perot transmission resonance, we could see actually at 8 micron the loss is about 4 dB per centimeter. This is the first fabrication. We hope that we could quickly reduce the optical loss by this germanium zinc selenide platform. And the optical mode in the long wave infrared is well confined in germanium part. So we also use the glow bar to do the transmission measurement. We see actually a wide transparency window from 5 to 13 micrometer. So this is the first time broadband transmission measurement using a glow bar. Actually, we see there are huge opportunity to utilize the full transparency window of the germanium. Okay, so what we could expect actually from this long wave photonics? I can give you an example. So this is the blood sample long-wave infrared FTS measurement. It gives signature about amide, some chemicals in our blood, like serum and plasma. So based on this transmission measurement, people has already used machine learning or statistics to do the cancer prediction. This, if we do the transmission measurement of our blood using FTS, it can give more than 90% accuracy in prediction if you have a tendency to have cancer or not. So this gives us very huge potential to do, for example, home health monitoring or like drone to environment monitoring in the long-wave infrared spectrum. Also, if we look at the perspective published in 2012, actually, in the long-wave infrared, there's almost no efficient laser source. So comparing to the near infrared, the micro-resonant cone is actually superb to other lasers or OPO or the different frequency generation. However, nothing is in the long-wave infrared. So I hope my presentation has shown you that there is huge potential of long-wave infrared photonics, and we have demonstrated ultra-high Q micro-resonator in the long-wave infrared for the first time that will make the Cal cone generation possible. And also, I briefly demonstrated the first germanium on zinc cyanide waveguide, which shows moderate optical loss, which could be future silicon insulator in the long-wave infrared. In the end, I would like to thank my advisors, Professor David Burkhoff at UT Austin and Professor Bjørnova Fimland and Astrid Aksnes at NTU. I also want to thank the financial support from the Research Council of Norway. Thank you.
Okay, so just now, and Dr. Ren has shared some nice work, especially in the the infrared low loss waveguide, and this is very important discovery and also important work for the future integrated photonics applications, and especially in the near infrared regime. And congratulations for this nice work, and let's discuss those work and the details with some of the comments later. Okay. So
Thank you.
Now let me introduce our second speaker, and Professor Yanting, and he right now is a assistant professor at the King Abdullah University of Science and Technology. Let me share the screen first. Share my screen. Okay. So let me introduce. Do you stop? Yeah. Do you want to continue? Yes. Let me introduce. Sorry. Give me a second to introduce. The second one. Okay. Yeah. All right. So let me introduce our second speaker. Dr. Wan is a assistant professor at the King Abdullah University of Science and Technology, and before that, he worked at Professor John Bauer's group at the University of South California, Santa Barbara, from 2017 to 2020. And then she played a key role in the Intel project on heterogeneously integrated quantum dot laser on silicon. Her research interests are mostly on silicon photonics, with special emphasis on the integration of on-chip light sources for optical computing. She has published more than 60 peer-reviewed research papers in Optica in very well recognized journals in the field of optoelectronics, and she has received many scholarships and excellent awards. For example, in 2018, she won the Pierce Young Scientist Award and a Rising Star in Women in Engineering Asia, and also Rising Stars in 2020 Women in ECS, and also in 2021, she won the Clio Linearly Innovation Prize, and also the 2022 Rising Stars of Light by the Light Journal. Okay, let's welcome Dr. Wan to share some nice and interesting works on the silicon photonics. Thank you.
Thank you for the introduction. Let me share the screen first. So can everyone see my slides now?
Just a second.
Sure.
I don't see your slide yet. Maybe I don't see it. Okay, now please go ahead.
All right. Thanks for the introduction. And hello, everyone. This is Yating. It's very nice to meet everyone virtually in the youth talk. So today I will talk about integrating on-chip light sources into silicon. Together, we will explore how to make light sources smaller and more efficient to the point where they can be integrated directly on silicon chips. So this has the potential to many application areas like data communications, biosensors, and most importantly, optical computing and quantum information processing. So I'm really looking forward to sharing our findings and progress with you. So let me start with a question. So probably you all know about ChatGPT, right? So these chatbots are amazing, doing everything from language translation. Like actually, you can also see this like the simultaneous translation for this use talk into for either Chinese or English. So this is some really important chatbots. But all of that computing power comes at a cost. And the cost is energy. So compared to a quick Google search, do you know how much more power is consumed in running this very powerful chatbot? It's about 10 times. And this energy is not free. So do you know how much is the cost to keep them just running for just one day? This is about $700,000 US per day. But it's not just these AI chatbots that are using tons of energy. The whole world is generating and sharing data like never before. So in fact, if you just look at this global consumer internet traffic in the last 5 years, it grows 3 times in just the last 5 years. And and this was with a very large compound annual growth rate is about 26%. And how much overall IP traffic in 2022? It's about 4.8 gigabit per year. And what does this 4.8 gigabit data mean to you? So here, everyone's very familiar. This is the Great Walls in China. So if you imagine every one of these gigabytes as a brick, and 4.8 trillion of this brick will make more than 1,000 Great Walls in China. So this is crazy. And where does all this data go? Data centers, right? So if you look at these data centers, they are very fancy, but they are also basically gigantic warehouses filled with computer process. And they are very power hungry. And actually, they consume about 2% of the overall energy worldwide. And do you know how much energy is used just for connecting these different parts of the data centers? It's around 30%. So that's where my work comes in. So we are trying to make these connections more efficient. All right, and if you just look at this figure, so we have 2 curves, right, with different slope, and that's a challenge we are facing. So while this is what we are very familiar with, the Moore's law, right, it doubles every 18 to 24 months. But if you just look at the other slope, which is much sharper, and that's the computational requirement, right? Like for just typical AI chatbots, and this is for ChatGPT, right? So there is a huge difference between the 2 slopes, and that gave us the critical bottleneck for electronics. So right, it just simply we cannot catch up. Right, the electronic hardware can just not catch up with the very rapid development of AI. So to put it into more perspective, think of it as just like we're trying to fill a water balloon with a firehouse, and the balloon, which is our computer hardware, is getting bigger and bigger, right? We are always getting more advanced in our technologies, but the fire hose, which corresponds to our data demands, is getting even faster. So what will happen? boon exposure, right? So our data needs just cannot catch up with our computer capabilities. So we get these two very big questions to ask. So how do we keep up with this growing data demands? And how can we do it without using up all our energy? These are the challenges we need to tackle as we continue to advance in the field of artificial intelligence and high-performance computing. Right. So as we know, so we just get a little back to the formulas. So the limit of the bandwidth in the electronic interconnect is determined by this formula, and where A is the cross-sectional area and L is the length of the electrical wiring. So while we can always make the transistors faster and faster by making it smaller and smaller, but if you just look at this formula, the electrical interconnect are lagging behind simply because of the simultaneous decrease in both the area and the length. So as a result, even get data transmission over 10 gigabit is getting more and more challenging. And that's not the end of the world. And here comes the big game changer. And that is, we can use light instead to transmit data instead of electricity. And there is a huge benefit, right? You can always transfer data much faster and with less energy and provide better signal integrity. And this is actually not new in the long distance communication. So like we in the long telecom communication, it's already a very mature technologies. But the challenge is that it's very, very difficult to push the length from the long haul communication to a smaller and a smaller distance. And what is the challenge here? As we go to shorter distance, the cost pressure also increase, right? So how can we make this feasible? How can we overcome this cost challenge? Probably we need to go back to the history a little bit, right? So if you just remember 1959 is a very important year for integrated circuits. So actually that's the first silicon IC. And that's the first silicon IC, there are only 2 transistors. But just if you look at today, like how many transistors do we have on silicon IC? Billions. Well, if you just look at lasers, so lasers is the very core element of our optical communication system. In our photonic integrated circuits, the laser is probably the most important part, right? So laser actually came to our world around the same time as silicon IC, but they are still nowadays very, very probably still at the component level and making them very big, expensive, and hard to scale. And so what is the magic formula that we can turn the electronic IC into photonics IC, right? It's probably all about silicon, all right? So it's all about bring the mature silicon processing that can give us high level integration, and process control, wafer level testing, and low cost packaging. So that's a $1 million question to answer. So how do we bring this Silicon Valley magic to the world of photonics? And the answer is staring us in the face. We just make electronic IC playbook and go to the path of integrated silicon photonics and setting our sights on high volume, low cost solutions. All right, so we have talked about why silicon photonics is important, but what is really exciting that it's not just a lab experiment, it's a booming industry. So, if you just this is just like the revenue growth of silicon photonics expected from 2020 to 2025. So it's about triple growth. And what does this mean? Just running from $1 billion to $3 billion in just half a decade. But don't think that's just a business gold rush. Actually, if you just look at exponential growth in academia, so it's also like you can see many people are very, very interested. So starting from Songrui and Burnett, and with the milestones many achieved in UC Santa Barbara, Intel, and IMAC, and again university, you see there is an exponential growth in published articles each year, and so we can see that it's really a hot research ticket. And you might think silicon photonics is all about, like we have talked about, in making our internet faster. But actually, it influences so many other areas, right? So LiDAR and AR/VR, and optical and computing, gyroscope, and biosensors. So whether you're entrepreneur or researcher, or just someone really tired of waiting for the Netflix to buffer, so keep your eyes on silicon photonics. It's not just a rising star. It could be very well be the future. From what we have just talked about for so far, so silicon is definitely a superhero for photonics, right? So it has so many benefits, right? Like very good CMOS control, high volume, and it provides a low waveguide loss that can be as low as 0.03 dB per centimeter. And it a variety of photonic devices are now standardized in the CMOS photonics foundries across the world, including like modulators, detectors, low loss waveguide, etc. But every superhero actually they have a weakness, and silicon is no exception. And in some aspects, silicon is quite bad for photonics, but because the most important part of photonics laser, silicon has nothing, it's just a very difficult to do for silicon. So compared to the traditional material to make lasers, like the 3-5, right, the direct bandgap. So you know the light generation is very efficient, but a silicon is an indirect bandgap material. So the way it generates light is really inefficient. So to give you a more perspective, so you know the best group 4 material, the special current density can be as high as 3,000, and the 300, yeah. But do you know what is the typical, like the value we expected for direct bandgap free material? It's just 0.1. So there is a 3,000 times difference. All right, and there are also other concerns in addition to lasers, for example, modulators, right? So it's just they can only work with certain wavelengths of light, roughly in the near infrared, and for other wavelengths, it's not possible. And finally, like silicon photonics are reciprocal, and that means they have a one-way system. They cannot reverse the direction of light, and means some very important components like isolators and circulators, they're just not possible. So as a result, like to overcome all these limitations, it's very important that we combine the silicon photonics with the direct bandgap free materials to make lasers and also allow detection and modulation outside the near infrared. So one way doing that is like people are doing for like many years is hybrid integration. So it's just like assemble individual pieces, like you do 3-5 devices and then you do silicon devices and put them together like a Lego set. And the flip-chip bonding is one very obvious example. And the advantage is obvious, right? You can optimize each part separately for their best performance. But the downside is also very obvious. It's like if you imagine building a Lego castle that as each brick needs to be aligned perfectly, right? That's very time consuming. So like each of the components, 3-5 and silicon, to align them together, it also takes a huge amount of time. And to ensure this kind of alignment accuracy, it costs a lot of money. Actually, as large as 90% of the total cost. So a different approach is actually called heterogeneous integration. So instead of assembling like Lego, so actually it's just like stacking layers of cake, right? So actually we bound the 3-phi into the pre-patterned silicon wafers at a pretty early stage. And then we can go to the wafer scale lithography to pattern the subsequent devices. So now seeing the alignment accuracy between the 3-phi devices and the silicon wafers are no longer determined by manual alignment, but actually they are determined by the wafer scale lithography. So that becomes much more efficient. It was so efficient that companies like Intel has turned into a billion-dollar business with just 1 decade of its inception. But there is also a limitation. So if you just look at the size of the 3-phi and look at the size of silicon, right, and look at how much the cost between this 3-phi and the silicon the largest available 3-phi substrate, typically around 150 for indium phosphide and 200 for gallium arsenide. They are both smaller and much expensive than their silicon counterpart. So while we have made a really great strides in this method, there's still some room for improvement. And one is that we can actually consider the direct epitaxial growth by monolithic integration. It's probably a more economically favorable option, and also it provides the most natural heat sinking. And the problem is that when you put very two different person together, they will have like a lot of quarrels. And when you push two different materials together to grow together, actually you encounter all these defects, threading dislocations, stacking force, anti-phase domains, and all these defects, even though they are pretty small in the very beginning, during the laser operation, they will grow larger and larger into this dislocation network, and finally there's a large decline of dark defects that seriously degrade the device performance. So actually, you can see that people try to grow quantum well laser on silicon like when in 2003, that's like decades ago. But if you just look at how much time they can survive, it's just less than 200 hours. And then in this scenario, we have another question to ask, like how can we improve 3-phi lasers on silicon by orders of magnitude if we want to pursue the direct epitaxial growth that is more economically favorable and provides better heat sinking? So the strategy here is that we actually deal with active region, and we want to move all the way from bulk quantum well and actually to quantum dot, similar to how quantum well replaced quantum wells. We want to replace quantum wells with quantum dot. So what is quantum dot? So you see this quantum dot of really small particles that act like this tiny box that can trap particles. And they are typically formed using this special process called self-aligning process using indium arsenide on gallium arsenide layer. And this layering process will result in structures that are so small that they confine particles in 3 dimensions. And this confinement change how the particles behave, and they give rise to a complete localization of electrons and holes, giving rise to this sequence of delta function like density of states, producing atomized degeneracy. So as a result, quantum dot do promise a lot of performance, like a really high temperature operation up to 220 degrees C and much lower stretch current compared to the quantum well counterparts. And more importantly, actually, the quantum dot is very famous for its line width enhancement factor, or we call alpha factor, right? So if you look at the typical quantum well lasers, it's about 3 to 5, but quantum dot is 15 times smaller. So what does this mean to you? So if you look at the alpha factor, it's very closely related to the critical feedback level, and 15 times smaller in our alpha factor will correspond to more than 50 dB increase in this critical feedback level. And that means that, so in quantum dot lasers, if you place 90% of the light back to the laser cavity, which would probably spill a lot of luster for many laser systems. But our quantum dot laser, you see, it's very stable. But for quantum wells, do you know how much reflection will cause this total coherence collapse? Just a minor 25 dB. So this is very important for data communication system because if you have like lasers, they are highly tolerant to feedback. You don't need isolators that are bulky, expensive, and add a lot of complexity to the packaging, right? So with quantum dot lasers, these challenges can all be largely bypassed. In addition, another important factor is the lateral diffusion length, right? So for quantum well, this value around 10 micron, but quantum dot is just 1 micron. So imagine in the quantum well, these carriers can move freely around in the Weber plane, and they can encounter these dislocation trap states and be trapped here. But a quantum dot, each quantum dot is nicely located in one area, so they don't have the chance to meet these trap states. So this is a more vivid example, right? So this is a very, very defective material. Like you see, all the red points refer to one defect. There are a lot of defects here. But the quantum dot, the density is much small, it's much denser than the defects. So even with all the defects here and here, it can only kill one of a few dots, and the majority of the dot, which is at least 2 orders of magnitude than the spreading dislocation density, they remain unaffected. So that makes quantum dot a super choice for materials where the high spreading dislocation density may be an issue. So this improved tolerance of defects that actually offer a lot of like record-long device lifetime in the lasers. So remember, we talk about for quantum well lasers, the best scenario is 200 hours. But we can easily hit to 800 hours in our first batch. And actually for most recent batch, we can give rise to a million lifetime at 80 degrees C. So you can see this quantum dot are much better than their quantum wells that has been developed for like decades. And that really underscores how advanced the quantum dot can be in the realm of silicon photonics. So there's a lot of recent progress of quantum dot devices grown on silicon, such as the sub-wavelength optically pumped devices and the sub-million threshold microring lasers. There's couple cavity tunable lasers and high-speed DFB lasers, the like isolation-free system demonstration, and also this 20 gigahertz Moloch lasers with high channel count and excellent RF performance. There's high gain, high saturation out of power amplifiers, and the quantum dot also turned out to be a very good material for photo detectors. The dot current can be like 3 times 3 orders magnitude smaller than the current germanium photo detectors on silicon. But in addition to all the improvement of material quality and individual quantum dot device performance, we are really actually very interested like how we can achieve this quantum dot active region laser emission back to the silicon, right? So we want to know how the transition will work, like from the 3-phi and through a taper and then go to the silicon waveguide. So actually, this is like not an issue for like typical indium phosphide heterogeneous integration, but now we're not working with indium phosphide based quantum well. We are actually work with GaN and based quantum dot. So we need different material system, and that's very different device design and the process optimization. So to do this process, right? We want to, the most important part that we want to taper the light from this like a hybrid mode and like overlap both the 3-phi and silicon and all the way through these tapers and to this silicon waveguide so that we can have this very efficient light transmission, right? So we start with this silicon part processing and open areas for bonding, and we bond the 3-phi materials and remove the substrate, and we like take care of the rest modulation for the detector part, and then we try to pattern this MESA, which actually like we spend a lot of time for this MESA process optimization. So we can ensure this, you see, very nice side wall, and so that we can form this very nice taper, which is here, so that we can taper the light from the 3-phi to the silicon. And this actually, we have to be very precise because this is the N MESA, right? N gas MESA is just 150 nanometer. And this 3-phi MESA is 3 micrometer. It's like 300 times larger. And we want to have a very precise control that we etch right at the N-gas contact layer. Okay, and after we finish this taper and we make this separate transition in N-gas, and then actually we can continue to passivate the devices, put P metal, N metal, and open via for pro metal. So this is the finalized cross section of these devices. So in terms of our first batch of devices, so it has a like decent like a threshold, thermal expression ratio, temperature performance, right? But actually, what I want to emphasize here is the modulation bandwidth measurement and the line width measurement. You see, quantum dot is always like have a problem with high modulation bandwidth. Even on native substrate, it's limited around 10 gigahertz for all these reasons, right? The skin saturation effect, etc. But like we already get a very record value of larger than 30 gigahertz, and this is actually achieved in a very, very long cavity, 800 micrometer. And we didn't apply any additional technique like basic coating, etc. So there remains a lot of room for further improvement. Another interesting thing is we measure the frequency noise, and we measure the line width to be just 26 kilohertz, and this is also an order of magnitude lower compared to typically solitary quantum well laser line width, which is several megahertz. So if you look at this table and compare the device parameters with work of and previous reported work, and we want to show that so laser with a silicon waveguide is perform much better for lasers without a silicon waveguide. That's we're really excited about, because actually it shows that actually the silicon has something to do the synergistic relationship with the quantum dot that can give us better performance than purely 3-5 quantum dot devices. And to put it into simple words, that means when you put lasers on silicon, you not only get a larger, better, and a cheaper substrate, you also get better lasers. So it's very good in the economic and also very good for device performance. So in collaboration with Intel, we're currently utilizing their 300 silicon photonics platform to create passive components, and then we can bound our quantum dot material. So Intel Lab has recently established a research center focused on integrated photonics for data center interconnects, and our project is one of the very interesting collaboration with academy and this industry to deliver practical solutions. So we believe that by switching from bonded quantum well epitaxial material, which they already achieved a lot of commercial success, to quantum dot on silicon structures, there will be a lot of very, very new opportunities for industry as well. And actually, when we go through all the way from hyper integration, heterogeneous integration, and monolith integration, it will also be very interesting for a lot of applications. If now we can put the lasers directly, like seamlessly integration with other silicon photonics components, that will have a lot of things to do for object computing, biochemical sensing, quantum information, optical LiDAR, as well as the dominant of the communication, right? So because the laser is off chip, it's not off chip, it's now on chip. So everything will be more efficient and cheaper, and we can probably achieve mass production of this method. And this is just this is something we are working on. So we are actually trying to apply this on-chip laser this process for applications like neuromorphic optic neuromorphic network. So the system is designed to process information in a way that mimics how our brain works. And our main focus is to increase the system's bandwidth, which is how much the data can handle, and also the energy efficiency, which means how much power it uses. And we are doing this by using quantum dot Moloch laser directly on chip with the cascade of microring modulators. So like I said, the important part here is that now the lasers are directly added on the silicon chips rather than attached separately. And compared to this conventional optic method, it will be more compact and cheaper, and probably more close to mass production. And also, like, we are also trying to work with CS people. So previously, like, photonics people don't understand CS, and CS people don't understand photonics. And we are trying to also improve the algorithms so that we can just use simpler photonic devices to deliver the same or even better performance. So, like we have worked. We're really interested in working this integration of lasers with photonics, and we're really interested to like collaborate with like people working in different areas, like for example, just mentioned like neuromorphic photonics, AI photonics, and also probably quantum information process people, so that we can actually, because we are device level, right? We are not application level. We really want to apply this kind of device technologies for different applications. So finally, and most importantly, I would like to thank all my students. Like now we have a 8-people team in KAUST, and also pretty international. We have people from Russia, from Mexico, from Canada, and also most people from China. So we're working together in this very exciting area, and also like we still collaboration with Professor John Bowers in UC Santa Barbara, and also we are so thankful for all our collaboration, especially to Dr. Haisen Rong's group at Intel for contributing so much to this work. Thank you for listening. That's sorry. Oh, sorry, I spent much more time than I. Sorry for the very bad time control, and thank you for your time.
All right. Very thanks to the Professor Wan's very nice and important talks, and also congrats to this very nice progress in the integrated photonics, not only on the quantum dots lasers, but also with the new architecture, which is mimic the brains as what you want to achieve for optical computing, which is very, very important. And this could be the future of integrated photonics, and hopefully with your effort, and maybe we can have those very nice integrations into a very solid mass production integrated photonics in the future for optical computing applications, right? All right, I'm gonna give you a certificate. I forgot to give you a certificate of Dr. Ren's the certificate, which is electronic certificate about your presentation. This is for you. But for Dr. Yeah, for Dr. Ren, and there's another one. Yeah, this is for Dr. Ren Dingding for your nice presentations here for the nice presentation. Okay. All right. So with that, we are going to move to the third presentation, and the third presentation is from Dr. Zhao. And Dr. Zhao is from McGill University. Okay, I have been knowing Dr. Zhao about when I was a PhD. I think when I was a PhD student, we met many times in the international conference because we are working on the even more closer field on the gallium nitride based optoelectronics. So let me briefly introduce Dr. Zhao a bit. He is an assistant professor right now in the Department of Electrical and Computer Engineering at McGill University since 2018. His research includes the molecular beam epitaxy of 3,5-nitride nanostructures and their application to the photonic devices. He has published more than 90 peer-reviewed journals and over 90 conference presentations, including many invited talks. Also, he has wrote many book chapters and received quite a few awards, including the Molecular Beam Epitaxy Conference Outstanding Paper Awards, and also International Conference on MBE Young Scientist Award, and also the North American MBE Young Scientist of Investor Award. All right, so with that, let's welcome Dr. Zhao for his talk about the Nanowire ultraviolet photonics devices. All right, Dr. Zhao, please go ahead.
Thanks, Haiding. I think you arranged the talk in a very interesting way, from longer wavelengths to shorter wavelengths. Now I'm talking about ultraviolet and
Exactly. Yeah.
Okay, let me share. Okay,
Oh,
so
Songrui,
can you
we
guys
couldn't see
see?
your video. Did you turn on your video?
Yeah,
We
we can
cannot see
see
my
all
video?
video now.
Can you
I
see me
can see
now?
the video.
Okay,
Okay.
that's nice. Yeah, sure.
Okay. Yeah, please go ahead.
Hello everyone. I think it's really great to be here to share some of the recent research done by my students. And compared to the previous talks by Dr. Ren and Dr. Wan, and my talk is actually slightly different with elements on materials. Because from my perspective, so materials are really the first step to devices. So in fact, a lot of research effort of my group is really on material development, improving material quality and etc. Okay, and in this talk, actually, I'm going to show some results on the nanowire ultraviolet photonic devices. Okay, let me bring the laser pointer. Okay. So here's a brief outline. So I would like to discuss why everyone should care about ultraviolet photonic devices, and then I'll talk about surface emitting lasers use a very special technique, basically low temperature selective area epitaxy grow nanowires. And then I'll talk about vertical UV LEDs based on nanowire assisted nitride on silicon template and conclusions and outlook. Okay. So UV light, probably as we all know, so ultraviolet light is very important for many applications like this water treatment and disinfection. Okay, and then from this kind of application viewpoint, so you prefer large surface area. So which means ideally you want surface emitting devices. And also from the human exposure viewpoint, you want shorter wavelengths. Okay, recent studies show that if you use very short wavelengths, basically you can just turn on the light all the time without damaging your DNA if the light wavelength is below 240, ideally in the 230 nanometer wavelength range. But problem is if you look at the current status, so mercury lamp is the most commonly used one, but we all know mercury is a hazard to both environments and human. And then for mercury lamp, limitation is really you cannot tune the emission wavelengths. You only have a few emission lines, right? And then if you look at the semiconductor side, so aluminum, gallium nitride, this alloy, so it's really the materials of choice these days. However, there are many challenges from the materials perspective. Okay. On the other hand, so if you look at the nanowires, which is basically a different material form, so they have a large or very large surface, like a schematic shown here. So in this kind of form, so you have a very large surface to volume ratio, so that when you grow this material, the strain can be relaxed very efficiently. Okay, so here what's shown is the critical thickness. Like if you grow this length, and then you have this radius, and the different numbers lattice mismatch. So I think the take-home message from here is that whatever lattice mismatch you are facing, you can always find a critical radius, so that if you grow very, very thin nanowires, like very narrow ones, you can always grow very, very long. So this is very important. It means if you use the form of nanowires, essentially you can have, high quality materials on any substrate, for example, silicon. Okay. And in fact, if you look at literatures over the past 10 years, there are really many device breakthrough use nanowires. For example, this very short wavelength aluminum nitride nanowire LEDs with very, very good IV characteristics. So this turn on voltage is only limited by the band gap. And then have some other applications on photocatalysis, like you can basically convert solar energy to hydrogen, solar hydrogen conversion. And most importantly, you can have electrical injected lasing use semiconductor materials. Okay. And In this talk, so I will talk about some of the recent research from my students. So the first one I want to share is on this kind of surface emitting UV lasers by epitaxial nanowire photonic crystals. Okay, so here shows a schematic of the growth. So basically we use a gallium nitride on sapphire template. And here we use titanium as a mask. So essentially you can open many holes on this titanium mask. Okay, so that in this case you can control the nanowires are really formed in this opening area. Okay, so with this technique, actually you can have a very beautiful well-ordered nanowire arrays with the same height and the same radius, for example, shown here. So well, all these different SEM images just shows different growth parameters. I guess I'm not going to describe all the detailed growth parameters, but take-home message is if you really control the growth temperature, like the growth parameters very well, you can really have very good quality nanowires. Like you can have any radius you want, you can have any height you want. So basically you can totally control it. Okay. And here is another example. So you can change, basically you can change the patterns. You can make the holes, nano holes are very far away from each other. Then you can have nanowires with different shape as well. Okay. So, and the interest part is here, actually you can control this size of this top surface very well. So why this top surface is very important is really because once you have this kind of nano column, right? So then after that, you can grow quantum wells, for example. So which means you can control the quantum well size in situ, or in fact, you can have quantum dots on this plane as well. So essentially you can control the size very well. That's why it's a very interesting and important control here, okay? So then with this kind of control, so we further demonstrated a surface emitting UV lasers by this kind of structure. So here's a schematic. Okay, so we have the nanowire arrays here, and this array arranged in a special way. So like you can see from here, seeing a square lattice. Okay, and here is two different points, gamma x, gamma m means the light can propagate in this in-plane two directions. And we also use the gamma point, which means at the gamma point, the light can really move very, very slowly, so that to the point that is essentially localized here. And another interesting aspect of gamma point is essentially the light can also be diffracted out at gamma point. So that's how you can have surface emitting lasing as shown here. Okay, so this is a band structure, shows well, this reduced frequency basically can give you the wavelengths you want. And then here is the in-plane field distribution. So you can see the mode is really in the array. Okay. And here is well, SEM image, large scale. So in this kind of devices, the size is about 100 micron to 100 micron. And here's a high resolution SEM image. And here's optical image. Basically, if you zoom in this square, you have nanowires like this. And if you further zoom in, you'll have some nanowires like this, okay? And then we used another laser, very short wavelength laser, 213 nanometer, to pump this kind of structure, okay? And you can see if you grow the nanowires, follow this design, you can see a very, very strong and natural peak, okay? But if you just grow like randomly arranged nanowires, like make the spacing very big and does not correlate to the band edge mode, then you just can have a very weak emission, okay, and broad and weak. So this is a first indication that okay, now we have light amplification because of this photonic crystal cavity. And then we performed a lot of detailed characterizations. For example, you can use laser to pump, right? You can change the laser pumping power. So if you pump the material hard enough, you will have this kind of narrow peak, right? You can see the intensity increases very fast, and also the longwave becomes very narrow. Okay? And then if you look at the light output versus the pumping power density, you can see a clear nonlinear behavior. So you have a kink here, which is the threshold. And this threshold is below 10 kilowatt per centimeter square, okay? At this point, so you still cannot conclude, well, you have laser. And the next step is, well, as a minimum, you want to plot this into a log scale to see this kind, if you have this kind of S shape or not, like mimic a S shape. So this part is spontaneous emission. So then you have light amplification, superlinear. Then you have another linear regime. So this can be evidence for lasing. Okay. And then shown here is the longwave reduction and stable lasing operation wavelengths. And then we compared with, well, many previously reported UV VCSELs or near UV VCSELs. So VCSEL means a vertical cavity surface emitting laser. So in this kind of laser, you need a bottom mirror. So essentially you have mirror in the bottom, you have mirror on the top. So then the light just bounce back and forth, then go out from the top surface. Okay. But in this case, the problem is if any of you work on this kind of VCSEL structure, so this bottom mirror, top mirror are very difficult to make. Okay, you really need a very, very high quality material. If the material quality is not good enough, you have a lot of optical loss, for example. Okay, so as a consequence, if you look at the conventional UV VCSELs, the threshold is really, really high. Most of them are around 1 megawatt per centimeter square. Okay, and in this work, well, we essentially bring down the threshold by almost 2 orders of magnitude on below 10 kilowatt per centimeter square. Okay. Right. So now the next topic I'm going to discuss is vertical elegant UV LEDs. Okay. So previously I have shown, okay, you can use nanowires as the emitter directly. But now we try to use nanowires as a different way to help the development of certain challenging photonic devices in the UV range. So from the LED's perspective, so if we know like the typical LED structure, and maybe I just show here. So you have this P metal contact and N metal contact, they are on the same side. So essentially, if you have the current path will be like this. And we know current always want to go to the shortcut. So as a consequence, so you have current crowding here. So which means in this region, you will have local heating. And this local heating will actually degrade the device performance a lot. So which means ideally you want to put one metal contact on top and then another metal contact in the bottom, and then you do vertical injection. So that's the ideal scenario. Okay. But unfortunately for ultraviolet range, the shortest wavelength is really only down to the 280 nanometer. Okay. There are many, many challenges. So ideally, if you think about the light emission perspective, right? So ideally, if you want to have vertical current injection devices, you want a transparent substrate, right? And also you want that transparent substrate is conductive. However, if you check all the commercial substrates available these days, they don't meet this requirement. For example, sapphire is transparent, but it's not conductive. Gallium nitride is conductive, silicon carbide is conductive, but they're not transparent in the very short wavelength ultraviolet range. So which means you have to remove this substrate, use high power laser, okay? But use high power laser to remove the substrate is a problem. It will damage the quantum well and other device layers. And moreover, if you want to make a really short wavelength UV LEDs, like I mentioned earlier, like below 240, which is safe to human exposure, and then you have to use aluminum nitride. And then it's really a nightmare if you want to do laser lift-off involving aluminum nitride, okay? So that's why, so it's really limited by 280 nanometer these days. And then silicon, we know silicon is a very, well, appealing material from many, many reasons. And for vertical LED viewpoint, so silicon can be removed very, very easily by chemical etching, okay, or much easier compared to using high power laser. But then the problem is if you look at device demonstration, so you have to have very thick aluminum nitride layer and which is insulating. So in the end, you are still doing this kind of lateral current injection. And also, if you look at the characteristics, well, terminal voltage is high and the shortest wavelength remains at 256 nanometer, okay, and this bilateral injection. Okay, so the problem probably many of you have already guessed, right? So it's well known that if you grow aluminum nitride on silicon 101, for example, you are facing a very large lattice mismatch, 20%, and also thermal mismatch. So as a consequence, you have cracks and highly dislocation densities, etc. And then people really have been working very hard trying to improve the quality of aluminum nitride on silicon. For example, they use the pulsed flow. So basically, it's a technique that you can modulate nitrogen supply and aluminum supply so that you can improve the material quality, or epitaxial lateral overgrowth. So which means you can make some patterns and then you can make this kind of layer coalesce. Okay. But the problem is whatever technique you are using, you have to always use a very thick aluminum nitride layer. Okay. Excuse me. And also, so this growth process is very time consuming. So if any of you doing growth, you know, if you do gallium nitride, the growth rate can be very high. But if you grow aluminum nitride, so the growth rate, even with emulsivity, is not very high. So it's a time consuming process. And making this kind of patterns is also time consuming and cost consuming as well. Okay. So then we like to propose some very simple approach. Well, that's basically something I'm always pursuing. So ideally, you want to just get a wafer, right? So then you dump this wafer into whatever material growth reactor, then you get the material you want. Okay, so that's the goal we want to achieve. So in this case, what we can do is we can start with the nanowire. Okay, as I mentioned earlier, so nanowire, well, it can be dislocation free if you grow long enough or above certain thickness. Okay, so then we start with silicon substrate. So this is something you just throw into the MB reactor, and then we grow nanowires. Okay, and here's a read pattern. So read pattern is basically a diffraction pattern. Okay, and you can see basically to monitor the growth in situ. So here you see many bright dots, indicates you have these nanowires formed. Okay, and then we start to grow this aluminum nitride on top. And of course, so then aluminum nitride will become coalesced. And in this case, if you check the rate, so these dots are connected. So meaning you have coalescence. Okay. So then if you keep grow this layer thicker and thicker, so essentially you can have a very beautiful streaky read patterns. Okay, if you count lines, well, I will not talk about details, but basically this kind of feature, right, like this line shape and the two different orientation, you can see this kind of reconstruction. So meaning you have a very, very good surface, okay, a smooth surface, and also it's a aluminum polar surface. Okay. So here's an optical image, and well, actually this image may not be a good one because there is no contrast. But if you move around, so you really don't see any features optically. Okay, and this is a wafer. You can see it's very uniform, and you don't see any colorings, means the thickness is uniform. So here's a SEM image. So basically, you can use the electron, which well inject electron to this material. You can see the secondary electron, you can get this kind of image, and you can see a very, very smooth surface. Okay, and here's the TM image. So it's essentially you use another technique to use electron to examine the material. Now, if you look at the cross section, so those are nanowires, okay, and you have aluminum nitride here. You have some coalescence boundaries, but most important thing is coalescence is almost complete within this layer. Okay, and this layer is very thin. From here, you can see it's only around 200 to 300 nanometer, which is actually one order of magnitude lower compared to the previous epitaxial lateral growth use patterned silicon substrate. So here is a atomic force microscopy image. Basically, it's a technique that you can examine the surface, like how smooth the surface or how rough the surface. From here, this roughness is very low. It's only about 0.4 nanometers, so it means you have a very, very smooth surface. Okay. And then another thing, typically from the material development viewpoint, is for nitride, for this specific material, you want to know this material if it's ended, the top layer is aluminum or the top layer is the nitrogen, which will actually change the material properties or electrical optical properties by a lot. Okay, and then a technique is you can use a potassium hydroxide to the etching, and you see this kind of hexagonal peaks. Okay, so which means, well, this is aluminum polar, so which means the most top layer is aluminum. And to confirm this, we have done high resolution TEM. So you can see those bright atoms, okay, aluminums, and then this dark circles, nitrogen. So from bottom to top is the growth direction. So which means, so this material is ended with aluminum on top or aluminum polar. So we next use a very short wavelength laser to extract this material to check the optical properties. Okay, so this is a technique called photoluminescence. Okay, basically from here you can see a very strong emission around 210 nanometer, which correlates to the band edge emission of aluminum nitride. And another important feature I should emphasize here is this UV range. You don't see any other emission. So this is very, very different compared to the previously reported aluminum nitride IP layers, either on sapphire or on silicon. So they always have a defect emission in this wavelength range. But our photoluminescence shows really very, very clean spectrum. And this actually is even better than the commercialized aluminum nitride wafers. And then we further used the Raman spectroscopy to check if aluminum nitride on silicon is relaxed or not. Because we know silicon has a large lattice constant and aluminum nitride has a small lattice constant, then you have tensile strength. So basically this Raman spectrum is a technique that you can check the phonon characteristics, which is related to the lattice. And if you check this phonon peak here, and it's at this number, so this means aluminum nitride is relaxed. Okay, so this is very important. So then to make devices, you have to, for example, if you want to make quantum wells, right? So you have to have nitride-based material with different band gap. Okay, so in that case, you want to grow aluminum nitride, aluminum gallium nitride. So again, so we use this template as schematic shown here. So silicon, nanowire, aluminum nitride template. On top, we grow aluminum gallium nitride. So I'll skip the details, but you can have very smooth surface and the streaky red pattern, so it means the surface is smooth. For example, SCM image shown here and AFM image shown here. So basically you have a good surface. And then you want to check, okay, now if we really have aluminum gallium nitride with different aluminum content, right? So to do this, we grow many different samples, right? Then we again use this photoluminescence technique to check what's the photoluminescence peak. And you can see the emission peak changed from 300 to 242 nanometer. Okay, and then if you further convert this wavelengths, right, you can estimate aluminum content, which is in the range from 35 to 70%. So which means you can basically widely tune the aluminum content range in this alloy, or another way you can change the gallium content in this alloy. So basically you can have material with different band gap energies, and then later on you can use them to make devices. Okay, but before to make any devices, the first important thing is you want to make sure, okay, you have the correct doping. And then for this kind of material system, the p-dap doping is very, very critical. That's why we spend lots of time to understand the p-tap doping to this algon IP layers on this aluminum nitride on silicon template. So here, well, it's again, PL technique we always use, and with different magnesium doping concentration. So if you look at low doped sample, so this is a band edge emission, okay? And if you increase magnesium doping, you start to see some signal related to magnesium transition. So which means you have magnesium doped. Then if you dope further increase very high doping concentration, now you start to see some impurity band transition. This is something you want to avoid. Okay, so that's why for later device demonstration, we really use the moderate magnesium doping. And then we also want to check, so because we claim, right, so if you put a nanowire template, it can help a lot. And then we are just curious to say, okay, if this really helps magnesium doping or not. So then we did a magnesium doped aluminum gallium nitride layer directly on aluminum nitride. Okay, so it's this curve. And you can see, in fact, you don't see any magnesium related transition at all. You just see defect emission. Okay, so that is the evidence. Okay, so with this Nanowire template, you can really improve the quality of the material, okay, and improve the doping as well. So then for the device demonstration, so what we really show here is the vertical device, but as the initial demonstration, we used a very simple structure. So that's the very simple double heterostructure and schematic shown here, okay? And N-type doping concentration, P-type doping concentrations are shown here. And we have metal contact in the bottom. So you can dope this aluminum nitride, okay? So that's what, so then you can have conductive template essentially. So that's why you can put one metal contact in the bottom, another metal contact on the top. Okay, so you can have vertical injection. So this is the fabricated devices. So all those squares are the devices. Okay, and then we just measured light emission under different injection currents with different devices. For example, here if you change active region, which means aluminum content in this layer, you can have light emission from different wavelengths and all the way down to 247 nanometer. And this is on silicon, and this is by vertical injection. Okay. Although you may say, right, so silicon is highly absorptive in this range. Yes, but silicon can be removed. So which means, well, at least this is the first step. So if you remove silicon, if you use more conventional quantum wire structure with, well, complicated device design, in principle, you can have high power devices through vertical injection. Okay. Right. So in the end, I want to really point out, although here device demonstration is really on vertical UV LED, but in fact, you can actually do a lot more stuff. Like in the photonics area, you can have quantum emitter or second harmonic generators on silicon, use this kind of aluminum nitride on silicon template. And you can actually have power devices or high frequency devices on silicon using this kind of aluminum nitride on silicon template. I guess I'll stop here, and I'd like to thank my students, collaborators, and the funding support, of course, which actually is very important for this kind of material development work. And if you are interested in our work, you can send me email and we can discuss. And thank you for your time.
All right, that's very nice talk, and it's like we are, as Professor Zhao just mentioned, we are moving from long wavelengths, right, to the visible, and now to we just enjoyed some interesting talks about the UV, especially in the very deep UV, like close to about 200 nanometers, and Professor Zhao has been working on this field for quite a while, several years, at least 7 years on this field, and they have made quite nice progress in the nanowire, in the UV photonics, in the shape of nanowires, and that's very nice. Okay, all right. So this is a certificate to you about for the great contribution to our platform and also very nice talk. Thank you. And all right, with that, and I'm going to move on to our panel discussion. So may I ask for everyone, Dr. Wang and Dr. Ren, to show up, and let's have some panel discussions about photonics. And we may also have some questions. Probably we're gonna discuss together on this interesting topic about the photonics, and also what we can do together in the future. Okay, in the future. So all right, can you see the slides? Where's the slide? Hello, can you guys see the slide? Hello?
Yes. So
Hello.
the introduction slide.
So, all right. So, Dr. Wan, are you here?
Yes, I'm here.
Okay, so Ding as well as so I wanted to have some questions to each of you, and because we started with the long wavelengths, okay, to the very long wavelengths infrared, and now move to the visible from Dr. Wang, and now goes to the Dr. Zhao about the UV photonics. I want to ask quite a few questions, especially I feel like most likely Dr. Zhao has been developing the UV photonics, maybe similar for those nanowire structures or nanowire optoelectronics. We can also make visibles. Actually, what he has making on the some of the photonics on silicon platform can be exactly immediately, not exactly immediately being used for Dr. Wan and Dr. Ren onto integration with the silicon platform and also the photonics you are developing. So I think we are all sharing the same view that silicon is important, and the silicon can be not only the supporting for the active devices like lasers, LEDs, and those devices, but also can be a platform that to integrate all of like a long wavelength device to visible device, and then move to the UV devices together, right? To move on to the silicon platform. So this is really like I didn't when we planned this topic today, and I didn't expect this could happen. I found that now we can actually write a proposal together to
Good point.
work on the silicon photonics, for example, by integrating the nanowire, DPUV, nanowire visible, and then nanowire long wavelengths. Indium nitride can be long wavelengths waveguide, right? Can be very long, go to 1.9 micrometer long. So it's a very good topic. What do you guys think about this kind of ideas?
I think it's first we need to define what is silicon photonics. Like if we just talking about SOI, so like silicon is like silicon waveguides like cannot support is not a very good material for UV. But if silicon nitride, so actually sometimes people like in the silicon photonics foundry, they also provide silicon nitride, and in a very in a broader definition of silicon photonics, it also includes silicon nitride. So definitely, like it actually can work with from like shorter wavelengths all the way to the longer wavelengths.
Yeah, agree with you. So how about the Dr. Ren?
Oh yes, I agree with the. I mean, this is a great perspective. Because, for example, as the Dr. Wan and Dr. Zhao said, silicon can be a starting point, right? And then basically you can do epitaxial growth of 3-nitride and 3,5. And what's the opportunity for for silicon is like they can also grow, for example, in gas, basically, because the difficulty for long-wave photonics is multi-photon absorption, which heavier element is always better. You have basically lower oscillator frequency. That means you can go to longer wavelengths. So we are interested in doing some like very heavy element like indium, gallium. So this stuff could really 3.5 on silicon would be really something important for integrated long-wave photonics. That's correct. Yes.
Okay. Yeah, because we are all sharing a silicon platform, and now we are all building using different techniques, right? Not only probably like we can use quantum well epitaxy, as also Dr. Wan mentioned. We can use MOCVD growth, or we can also do some epitaxial growth, what Dr. Zhao has been doing by growing nanowires on top of the silicon. But also we can do some on-chip bonding and on-chip integration by connecting those passive devices with the active devices to form those interesting and important integrated photonics platform. And so I wanted to ask more about what's your view, like by not only just focusing on your own field, right? Because everyone is actually working on the different wavelength spectrums. So I want to ask you, if you jump out of the wavelengths you are working on, what do you think and what do you expect what we can do together to leverage the silicon platform? Because silicon cannot be an emitting device, right? But what do you see if we can really leverage the silicon or CMOS platform or CMOS compatible fabrication techniques to really like integrate many kinds of the active devices or passive devices made of the conventional 3.5, 2.6, or other type of the compound semiconductors. Is there any features for us to really pursue that to make the silicon photonics, the dream comes true? Like I want to ask you. So maybe we can start with Professor Zhao first.
Yeah, maybe I'm not the right person to answer this. Okay, my view is, first of all, I think silicon photonics is pretty broad. Okay, like depending on what you want to do, like a passive device, active device, and all in all, it comes to the application, like the chip in the end you want to make. And my second point is like what you said, from a research viewpoint, right? So nanowires are interesting. You can do nanowires with lots of stuff like UV range, visible, right? Micro LEDs and longer wavelengths near infrared, as long as it's not limited by the band gap. But I think from research viewpoint, fine. And then if you really want to push this research to some real application, so that's a different question. It's always, to me, it's like first come, first serve. Like about 10 years ago, I worked on indium nitride, right? Longer wavelengths, around 2 micron on silicon, very fun. Well, sounds very, very interesting at that time. And but the thing is, you have 3.5 on silicon, right? So if I was an investor, I would not to find another material. If you already have something, it's working pretty well. So I think that is a very, very important thing if you consider, okay, what's the motivation of the research? If you just interesting, I want to explore, fine. But then if you want to push some real technology, then this is perhaps the most important thing you need to consider. Yeah.
Okay. All right. So Dr. Wan?
So I think nowadays people definitely believe that photonics is going to like replace electronics in certain places, right? Because like we talk during the talk that there is really limitation for electronics interconnect, and silicon photonics is really a very promising platform to really achieve these photonic integrated circuits. But how to do it is really a big question. So actually, I have been working on like direct partial growth for like 7 to 8 years, but then I decided that probably the material compatibility is really an issue. Like, right, if you want to grow 3.5 on silicon, it's really difficult, and not to mention the subsequent coupling is too difficult. So actually, then I like about 3 to 4 years ago, I switched to heterogeneous integration that we try to use wafer bonding, which is also the commercial success of Intel, right? So by wafer bonding, you can actually like add different components together. So currently, like I'm still working on like quantum dot lasers integrated with silicon photonics. We are still like working in the very preliminary stage. But actually, I think there are many very exciting work going on for other groups. For example, so my previous colleague from UC Santa Barbara, he's now in Hong Kong University. So their group just published a Nature paper about 3D integration in silicon photonics. And actually, like you just mentioned, silicon, if you want to like reunion like the shorter wavelengths, DP UV, and with the longer wavelengths together, I think silicon nitride is very interesting. And in that Nature paper, they actually do 3D integration so that you can combine 5 materials to provide gain, and then transition through silicon waveguides and all the way to silicon nitride circuits. And that can generate many interesting applications as well. So they demonstrate comb generation in a single platform, and also microwave, etc. So I think this is definitely one very interesting platform that is going on, right, to do 3D integration so that you can combine a lot of components, 3.5 for light generation, and silicon nitride for waveguiding, and ultra low loss waveguides, right? And another thing, I think another direction probably for silicon photonics is that they actually try to, from the growth aspect, they try to do like selective ever growth. So and this is also another my colleague still in use in the Barbara John's group. So unfortunately, I'm not the leading author in that, but I think they are doing a really great job, right? So actually they can grow the laser directly in the pockets in about a couple configurations, so that they can couple the laser from the 3.5 all the way to the silicon nitride. And actually there is a lot of following work in China as well. For example, Wang Ting and Zhang Junjun's group in China's Academy of Science, and Hu Yunlou's group in UCL. So I think like those efforts are being actively served either by wafer bonding, 3D integration, or by direct architectural growth in about a couple configuration. And either direction is progressing quickly, but the motivation is the same, right? We want to achieve as many functionalities as possible in the silicon photonics platform, in a very broader aspect of silicon photonics that combine not only silicon waveguide but also silicon nitride, silicon oxynitride, so together. Like we talk about silicon photonics, actually we're talking about silicon substrate with different photonics functionalities. Yeah.
Yeah, I think that's a very good idea. That you just raised a very good point that for the architectural growth, we can do some selective area growth. Inside the selective area growth mode, we can pre-design the waveguides across the wafers and leave some spaces for the laser to fill in, right? To make like this is the light source in the hole, or in whatever shape, in the square shape, in the triangular shape, or what kind of shape you predefine the substrate, and then you use selective area growth mode to actually fill in some quantum wells inside the holes, and then this can be electrically pumped later on to make some electrode from the top, and then surrounding the active materials, or surrounding the 3.5 material, we can integrate some silicon or waveguides, or whatever waveguides you can design ahead, and before you load into the chamber to do the growth. And then this is like so-called really become two photonics integrations with passive and active together, and this is quite a cool idea. I think if the Santa Barbara, I think Professor Zhao can do this.
And also Kevin Lau's group in HKUST. Yeah, I think it's really depending on whether you're a mature person or you're a device person. For example, if you're a mature person, then you're more interested in selective ever growth. So you change, you like navigate the growth conditions to like so that you can directly grow the laser into these pockets and couple the light to the silicon nitride or silicon circuits. And if you're a device person, right, so you want to like leverage the process, right? You want to do heterogeneous integration by wafer bonding so that you can bond different materials and use process to combine these different components together. Yeah.
Yeah, that's a very cool idea. I think this is the best tricks or best ideas I learned tonight. Yeah, and all right. So, Dr. Ren, what do you think about this? Yeah.
Yeah, you have already a great perspective actually on silicon photonics. So I just want to highlight what silicon can now do, right? Basically, if we what it's missing actually, the actually silicon has central symmetry, so it doesn't have a high-2 nonlinearity, right? That's people has put a lot of effort to put basically like nonlinear second order presents a different frequency generation, second harmonics. They put like, for example, lithium niobate, right, on top of silicon. compensate because silicon doesn't, it can't have the this nonlinear process. So I think also there's an opportunity actually to think about what's missing, right? What silicon cannot do. For example, phosphoryphile lasers, because silicon cannot act as a light source. Also, silicon basically cannot work as efficient Ki2 nonlinear materials. Also, I think silicon has a really, really good optical transparency window up to 7 microns. But the thing is, once above 5 microns, the silicon dioxides become extremely lossy. When you're using silicon, we need to think about also the nitric oxide on the top, right? So that's have some impact from 5 to 7. But after 7, I think silicon photonics is a little bit challenging because the multiphonal absorptions, because silicon is not that heavy comparing to, for example, InGaAs or germanium. We need something material really heavy that can be combined with silicon. That's, I think, in my perspective, for a longer wavelength.
Okay, I see. That's very good. And because, as you mentioned, also we are talking about a lot about silicon. Can we just replace the substrates with some germanium with other substrates? Is that okay to, or even any other kind of substrates can be also used for this kind of integrated photonics, not only on silicon photonics, but also for integrated photonics. Do you think besides the silicon, what kind of substrate possibly can be used?
Yeah. Yes. So actually, for longer and longer wavelengths, heavier materials, higher crystal quality is better. So that's why we initially tried the epitaxy germanium, because epitaxy germanium, their problem is if it grows on gallium arsenide, there is arsenic background, right? Also gallium interdiffusion. It's caused a problem. If it grows on silicon, it's perfect, but there's huge lattice mismatch. So there is not a really good way actually to do epitaxy for this germanium material. So then you have to think about how to make device out of epitaxy. So that's the first. I think first solution is to find a way to do epitaxy, because it all makes the process easy. But if you don't have that opportunity, maybe we need to think about other alternatives. But yeah, it's a trade-off, right?
I see. So let me ask you a last question. Okay, the final question for Dr. Zhao and Wan. Besides silicon, what kind of template or substrate can be used for integrated photonics, and what do you see the future of the new substrates or the new templates beyond the silicon?
So probably Professor Zhao first.
Yeah. So
I really don't have much experience on silicon photonics, but like the one I mentioned in the end is maybe something interesting, because you can use silicon, like then you put a nanowire, then you can have any material use this silicon as a platform. You can remove silicon, or have a totally freestanding whatever substrate you want, or you can do this kind of integration to silicon directly, like maybe germanium, or maybe germanium tin, things like that.
Okay, I'd like to add something else. So, of course, there are many interesting candidates. For them, for people now interested in using silicon carbide because of their great thermal performance. Actually, I know there are a lot of like very nice achievements already being made in some institutions in Japan, especially NTT. But personally, I still have a very strong faith in silicon, and I think for a long time, like photonic integration is going to be on silicon. This is because the whole idea of photonic integration, like it is rooted in the same success that microelectronics people have already achieved, right? The microelectronics people have already achieved a huge success over the years by using the CMOS, very advanced CMOS manufacturing with silicon as a substrate. So I think the momentum will continue for photonics, and we're definitely going to leverage their success. And the success core is silicon substrate, definitely, because it's by far the probably the most commercially available option with a extremely low cost, very robust, and very large size is compatible with the current CMOS facilities. And as photonic device is pretty large, 65 nanometer line is already pretty great for photonics. So actually, we can just use the old electronics line for photonic device fabrication, and to be compatible with your existing process is going to be a good idea to just stick to the choice of silicon. So I think people are actively exploring different materials, for example, silicon carbide, for different purposes, right? If you really are looking at for thermal performance, or for example, silicon carbide is also used for some quantum features. So definitely you're going to explore different materials. But for photonic integration, I personally still have a very strong faith in silicon substrates. Thank you.
Okay, great. Thank you. So, Ren, do you have anything to add?
Yeah, thanks. I agree. Like thermal management is really a huge thing, right? Also, it remind me like also another thing is to we think about lattice matching, right? But also other materials could be as the intermediate buffer, which can basically break this lattice mismatch criteria. For example, some van der Waals materials. That could also be to, for example, put silicon nitride on top of a van der Waals material, and they put silicon, right, or other kind of material. So the lattice mismatch requirement for high quality epitaxy may not be a requirement anymore in future for heterogeneous integration. For example, in gas, right? In lattice match in phosphor, but still it could be epitaxy grow on silicon. For example, we have an intermediate epitaxy van der Waals buffer. That could be something I think to think about. Yeah.
I agree with you. So there's some emerging new papers developed or new techniques being developed by integrating the 2D material, the low dimensional material as the transition layer between the 3-5 material. Like MIT, the Korean scientist, the King, I don't remember the name, but I think you all know him about.
I know. The Korean guy, right?
This Professor Dingding Wan, right?
Yeah.
Dingding Wan, yes. I know. Published a lot of nature series
in just
papers,
in just 1 year.
But the question is still,
we all know him, right?
The question is still whether it's really van der Waals or it's through some defects, right? Still,
I agree.
Controversy.
I agree. I agree.
So at least
it's difficult to tell, right? Difficult to tell.
It's very difficult to tell.
It's inspiring us to actually we can have a really weak bonding, right? But the weak bonding is maybe good for the relaxation, right? Strain relaxation, everything is perfect. Yeah, it doesn't matter if it's from pinhole but it helps. So I think that's really something maybe we could think about. For example, 3-5 on silicon. I don't know, but could be a good opportunity there. Yeah. But it matters also to whether MB or MO3D.
Yeah, I think I would like to, maybe because of time limit, maybe I would like to conclude, and some of the thought we have sharing with each other, and we are brainstorming together about the future of the integrated photonics. Silicon always the mainstream of the study, right, in our field. No matter what, is because it's already a mature techniques to fabricate large scale, not only electronics. Hopefully in the future we can integrate with photonics and make it integrate silicon based or silicon photonics, which is very good, especially for mass production. And the second conclusion will be that we would like to integrate, because it's very preliminary. I think it's still in the very preliminary early stage of the silicon photonics compared with silicon electronics, right? Silicon electronics being developed for many decades, but silicon photonics is very still early, and we have many opportunities, and we are glad all of us, at least the 4 of us together, still working on this very exciting and important field. And hopefully, through this connection and sharing of the networks, and in the future, we can collaborate together, and may inspire the new generation of the young scientists working on the optoelectronics, and to see that there's many unsolved technically scientific problems to be solved on the architecture growth, heteroarchitecture growth of the active layers on silicon, how to manufacture the devices, fabricate the devices vertically, laterally, and also how to bonding or manipulating, or basically is how we can heterogeneously integrate many kinds of active devices onto the silicon or onto this nice platform for future silicon photonics or integrated photonics applications. And there's many material issues, mostly on the material issues, and then we have to overcome some of the physics and overcome some of the challenges of the manufacturers and also the fabrications. I think we have the future, and we have very good future for the future research, but also many challenges to be overcome. So I think that's my overall opinion, but we have actually, at least together, 4 of us, we are making a lot of effort, right, to pursue these goals about this silicon photonics, and hopefully we, through this ICAPS platform, we have shared many topics about deep UV visible to long wavelengths. It's a very good topic and to share with the audience. And now I would like to conclude this talk, and thanks Professor Wan, and thanks Dr. Ding, and also thanks Dr. Songrui, and for this very nice discussion and very nice sharing. And thank you very much. Yeah.
Thank you.
Okay. Thank you. Have a good night. Bye-bye.
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 Okay, super
啊，
nice.
辛苦啦，辛苦啦。
Yeah.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么